and welcome to our fourth video on an introduction to radio interferometry. Picking up where we left off in the last video, we were talking about filling in the UV plane. We basically said that one pair of antennas in a radio interferometer measures one Fourier mode of the sky, and that's not very useful. And so we use a multitude of techniques to fill in the UV plane and measure a number of different Fourier modes of the sky. But the UV plane never gets perfectly filled. If you take a real distribution of antennas, calculate all the baselines, where they land in the UV plane, apply any of the techniques, multi-frequency synthesis, Earth rotation synthesis, the UV plane never perfectly fills in, particularly for the longer baselines, so further away from the center of the UV plane. And so, if we're never going to get a perfectly filled UV plane, the question becomes, what do we do? Well, so let's recall what we want. We want to get an image of the sky. I, the brightness of the sky, is a function of L and M, which are effectively sky coordinates. If we had the Fourier transform of the sky, I tilde of U and V, it would be very easy to get I of L and M. It's simply a two-dimensional Fourier transform. You can do that in one line of code. You'd have your image of the sky. But again, that's not what we have. What we have is a sampled version of I tilde. And so this S here is what we call the sampling pattern. Think of it as a function that is either 0 or 1. It's 1 wherever we have a measurement in the UV plane, so wherever a baseline sampled, and it's 0 wherever we don't have a measurement in the UV plane. And so you can think of our measured data as the product of the true Fourier transform of the sky with this sampling pattern. And so what we want to do is get some intuition for what the effect of this sampling pattern is. And the best way to do that is via the convolution theorem of Fourier transforms. I'll post a link in the video description that will say a little bit more about the convolution theorem of Fourier transform. If you haven't seen it before, it might be worth taking a look at that. But if you have, let's just do a quick refresher. The convolution theorem says the following. Suppose I have two functions, a of x and b of x. I multiply those two functions together, and I want to then take the Fourier transform of the product of those two functions. The convolution theorem says this is equivalent to taking the Fourier transform of the individual functions and convolving them with each other. So this asterisk is a convolution operation. If you're not familiar with convolutions, I'll also post a resource in the video description with a bit of information about them. But the key here is that Fourier transforms do not distribute over multiplication. Right? The Fourier transform of A times B is not the Fourier transform of A times the Fourier transform of B. Rather, it's the convolution of the Fourier transform of A with the Fourier transform of B. And so let's write this in terms of the radio interferometry case. And so what we have is the product of two functions, the sampling pattern and the Fourier transform of the sky. So if all we had was the Fourier transform of the sky, I tilde, we would simply inverse Fourier transform it and get back our image of the sky. If we try and do that to our sampled Fourier transform of the sky, however, meaning we try and take the Fourier transform of the product of these two functions, well, the convolution theorem says that what we get is the convolution of the two Fourier transforms of the two functions. This second one, the Fourier transform of I tilde, is what we want. That's our image of the sky. But the Fourier transform of the sampling function, we give that a new name. So we call that the synthesized beam, give it the symbol little b. And so if we take the Fourier transform of what we actually measured, the sampled Fourier transform of the sky, we get the convolution of what we want with the synthesized beam. And this also has a name. We call this convolution the dirty image. Instead of being a nice, clean image of the sky, it's got this additional convolution in it. And just a reminder, we introduced a couple videos ago the primary beam. That was the pattern of one antenna's response to electromagnetic radiation from different directions on the sky. The synthesized beam is very different. Radio astronomers are not always perfectly clear what they mean when they say beam, and so it's sometimes worth asking whether you're talking about the primary or the synthesized beam. So to understand what we have when we say we have a dirty image, we need to look a little bit more at what the synthesized beam looks like. And remember, it's the Fourier transform of your sampling pattern. So exactly your synthesized beam depends on the details of your instrument, depends where your antennas are, how long you used Earth rotation synthesis, whether you used multi-frequency synthesis. If your UV plane is pretty well filled, then the synthesized beam is not too bad. It'll look at its center like a Gaussian. Most things wind up looking like Gaussians at some level. And so this central part we call the main lobe. And then typically there are concentric, maybe not always perfectly circular, but concentric side lobes around it. And so what the dirty image is the real image of the sky convolved with this synthesized beam. And so point sources, a source that is completely, truly unresolved, instead of looking like a point, will look like the synthesized beam. So it will get spread out to the size of the main lobe, and then there will be these low-level side lobe structures surrounding it. So if you've done optical astronomy, this is completely analogous to the point spread function that comes from your telescope, sometimes called the PSF. And if you have lots of sources on the sky, each one of them gets convolved with the synthesized beam, and you can get some complicated patterns where side lobes from one source add with side lobes from another, or side lobes from one source land directly on the main lobe of another source. It can get complicated. Also, if the UV plane is not well filled, maybe you only looked for a short amount of time, or you didn't use multi-frequency synthesis, or your antennas were in a very regular pattern. We talked about redundant baselines giving you limited numbers of modes in the UV plane. Any one of those things can lead to a UV plane that's not well filled. And then your synthesized beam can take some ugly structures into it. And so you can get side lobes that are not circularly symmetric or even elliptically symmetric. They can have point-like structure, star-like structure. And if you have a very redundant array, you often get what are called grating lobes, which are very strong side lobes in particular locations on the sky. And so the next logical question becomes, okay, well, if we want to get the true image of the sky, how do we account for the synthesized beam? The short answer is that you can't. Right? Our sampling pattern told us where we measured in the Fourier plane. It led to the synthesized beam. And so if you didn't sample somewhere and you had a 0 in your sampling pattern, you didn't measure that Fourier mode. There's no way to magically get it back if you didn't make a measurement of it. Put another way, that Fourier mode on the sky could have an infinite number of values and you'd get the same dirty image because that Fourier mode is missing from the dirty image. And so in my field of 21 centimeter cosmology, we often just work with dirty images. We say, that's my closest representation of what I truly measured, and what I really want to understand is what I truly measured. But if you want to get a good-looking image of the sky, there are various techniques for doing that. Those techniques we might call deconvolution techniques, where we're trying to account for the effect of the synthesized beam. But again, fundamentally, in order to remove the synthesized beam, we have to introduce new information. We have to put in some sort of information about the Fourier modes we didn't measure. And typically, we introduce that information by making assumptions about what the sky is supposed to look like. And so the two most common deconvolution techniques, although there are many others and there's many flavors of these techniques, the first is called clean. Clean doesn't actually stand for anything. It's not an acronym, but it's almost always written in all caps. And you can see the name follows from trying to clean up the dirty image. What clean does is assume the sky is made up entirely of point sources. And so our dirty image is just a sum of lots and lots and lots of point sources of different amplitudes, all convolved by the synthesized beam. And if you make that assumption, then you can use an iterative deconvolution process to basically try and undo the synthesized beam and get a model of the sky that is composed of nothing but point sources. And so, as you might suspect, clean does pretty well when the sky is composed of point sources, but if you're looking at large, diffuse structure, you need to make some modifications to this algorithm to have it really succeed. The other approach goes by the name of maximum entropy, and maximum entropy approaches assume that the sky is smooth, so sort of the opposite of clean. Maximum entropy has a nice mathematical foundation, it's well understood, but in practice, tends not to work quite as well as clean. And so even though clean, again, is an iterative algorithm, it's nonlinear, there's not a real great understanding of its error properties, it's the one that's most commonly used because it makes images that look pretty good. And so let me conclude just by reiterating, any deconvolution approach is making assumptions, or introducing new information to the problem to constrain the Fourier modes that are fundamentally unconstrained because we didn't measure them. And so these algorithms can make good-looking images, and if the assumptions you introduce are reasonable, then those are physically motivated images, but fundamentally, they're not representations of what you measured with the interferometer. And so again, in my field, 21 centimeter cosmology, we often simply work with dirty images rather than introduce information whose exact statistics we don't necessarily understand.